Okay, take a seat, please. Okay, good morning. Dr. Tani couldn't come here today, so I'm gonna substitute for him. And you probably know me. My name is Shima Musavi. I have a PhD in control, and I do some research in Professor Frazoli's lab. And today, I'm gonna talk to you a little bit about, I can say, one of the most difficult part of this course, the control system theory, that is Nyquist condition. So this is not, this is a bad news, maybe. But the good news here is that it is the most useful method that we can use in, for a very general system. So far, you have become familiar with some methods and with some tools in control system theory. For example, you are familiar now with state space representation, with transfer functions, with Rose-Hurwitz criterion, root locus, and body plot. I know that Dr. Tani started this topic last week, but it was not finished. But he decided to, continue it himself in the next week, in the next lecture. So I start a new topic about the Nyquist method. And for any other method, there is a set of rules that you can follow and do everything about it. There is a set of rules, for example, for root locus. You can follow them and you can draw your plot, okay? But for Nyquist plot, it is a little bit different. There is no certain set of rules to sketch a Nyquist plot. And so this is not a nice method. This is not a simple method. So what we should do here is that we should be careful that this method is very useful. And when other methods, I can say that all of other methods can be misleading in some cases for some complicated transfer functions. And they cannot work in every circumstance. But when you get in trouble with some complicated transfer function, you can trust this method. And so this method is very useful. It gives you the correct answer for a very general, for a very complicated system, okay? So it is not nice, but it is very applicable. Okay. But before I want to get into the details about this new method, let's review some notions that you have learned in this course. We know that a system is a mapping between some signals, some input signals and some output signals, okay? Okay. And we know that a system can be represented by a set of differential equations. And it can be represented by in the state space form. Okay? But in this course, we have focused on a certain set of systems which are the linear time invariant or LTI systems. And the systems that have only a single input and a single output, and so we call them a seesaw system, okay? The LTI system has this property that it can be represented by a transfer function. For example, we can represent a system here with a transfer function L of S, and we have a single input U and a single output Y here. And in this way, we can get rid of solving differential equations, and we can do anything by just some simple calculations, some algebraic calculations like multiplication in the frequency domain, in the Laplace domain, okay? So The transfer function L of S is a rational function which has a numerator and a denominator, okay? And both of them are polynomials which are written in S, and we call the denominator D of S a characteristic polynomial, which is the same as the characteristic polynomial that is obtained from the state space representation of the system. I mean, x dot equals to ax plus bu, and y is equal to cx plus du. Okay? So the poles of a system are the zeros of the numerator, and are the zeros and the roots of denominator, and the zeros are the roots of the nominator of the system. Okay? And the LTI systems have this property that if we feed them with a sinusoid as an input signal, then we can get a response, an output, which is a sinusoid of the same frequency in a steady state. Okay, and these two signals are both in the time domain. Okay, but with different magnitude and with different phase. The magnitude is the multiplication of the magnitude of the input signal and the magnitude of our frequency response at that specific frequency. And the phase is the sum of the phase of the input signal and the phase of our frequency response at that frequency. Okay? This is just for a sinusoidal kind of input signals. Okay, but what can we do for other types of input signals, for a very general kind of input signals? We can say that for any input signals, we can do everything. We can find the response of the system very easily in the Laplace domain, just by the multiplication of the transfer function and the Laplace transform of our input signal. Okay? So everything is very simple in this domain. So one of the most basic and the most important properties of a system is its stability. And it is one of the properties that we should make sure about it at the beginning when we deal with a system. What is a stable system? You know that a stable system is a system that for any input signal, its output, its response does not blow up. But when we have the transfer function of a system, how we can figure out if the system is stable or not? Just by looking at the poles of the system. And the poles do matter for this purpose. Okay? So we say that a system is BIBO, bounded input, bounded output stable, if all of its poles are in the left half plane. Okay. So what we said in this part is just for an open loop transfer function, for an open loop system. We did not do a feedback yet. We did not close the loop like this. Okay? But when we do a feedback, when we close this loop, then we have a closed loop system, okay? So, what is the benefit of using feedback in our system? You know that it has a lot of advantages. For example, in this way we can make an unstable system stable. And moreover, a feedback control system can handle the uncertainties in the model of the system. Moreover, it can reject external disturbances, and so we can get the desired response when we do a feedback, when we have a feedback. Okay. But now the transfer function of our system would be different. How we can compute the transfer function of this closed loop system? By using the transfer function of the open loop system L of S. Okay? We know that the closed loop transfer function between the reference signal R and the output signal Y is given by KL of S over 1 plus KL of S. And it is also called the complementary sensitivity function. Okay. So what is the pose of the closed loop system? We said that the poles are very important to figure out the stability of the system. And now what we want to know is what we want to know is that how a certain system behaves when we close the loop, when we do a feedback. Okay? So we should look at the poles of the closed loop transfer function. But what are the poles of the closed loop transfer function? You know that you should find the roots of the denominator of the transfer function, that is 1 plus k L of S. Okay? So the closed loop poles, we said that the closed loop poles are the zeros of the function 1 plus k L of S. But what is 1 plus k L of S? If I write L of S as n of S over d of S, okay, then we can say that the closed loop transfer function is 1 plus k L of S would be d of S plus k n of S over d of S, right? So this is a function that has a nominator and denominator, okay? So the roots of the nominator, which are the zeros of the function, are the closed loop poles, are the poles of the closed loop transfer function, okay? But what about the zeros of the denominator? You can see that the denominator here is quite the same as the denominator of our open loop transfer function, right? So the poles of 1 plus k L of S are identical to the poles of the open loop transfer function. So we can say that the zeros of this function are the closed loop poles, and the poles of this function are the open loop poles, okay? Right? So we can say that the closed loop system is stable if all of its poles, if all of the zeros of the function 1 plus k L of S are in the right half plane. Okay, so far so good. Okay. In this part, let me remind you the phase rule and the magnitude rule. Consider a complex number in the complex plane. Say for example, S naught. And S naught, for example, it can be on the imaginary axis. For example, S naught can be J omega naught, somewhere here. Okay? And here we want to compute the transfer function for this point. We can write our transfer function like this as a multiplication of some terms S minus Zi over the multiplication of some terms S minus Pi's, where Zi's are the zeros and Pi's are the poles of our system. Okay? How can we compute our function for this point, for this specific frequency, for example? A simple way to do that is that we can draw some vectors from zeros and poles of the transfer function to that specific point, and then we can say that the magnitude of our transfer function at that point, for that number, is the multiplication of the magnitude of these vectors drawn from the zeros over the multiplication of the magnitude of the vectors drawn from the poles. Okay? And what happens to the phase? What happens to the phase of our transfer function in that point? We can say that the phase of our transfer function is given by the sum of the argument of the vectors drawn from the poles minus the sum of the argument of the vectors drawn from zeros. Okay? Well. So, in the analysis part of this course, what is our objective? Our main objective is to look at the open loop transfer function and then figure out what properties our closed loop transfer function, our closed loop system will have, just based on the properties of the open loop transfer function. For example, just based on the frequency response of the open loop function, or based on the zeros and the poles of the open loop transfer function. We want to infer something about the closed loop system in this way, okay? So, I said that the stability is one of the most important property here. For the stability analysis of a closed loop system, we can use some methods. For example, we have Rose-Hurwitz criterion. That is a mathematical evaluation of stability of a closed loop system. And you know that in this method, we consider the coefficients of the characteristic polynomial, and based on them, we form a rows table, and then look at its first column. Then if there is no sign change in the first column, then we can say that the system is stable. Okay, but it is based on some mathematical calculations, some mathematical computations. On the other hand, there are some more geometric, some more graphical methods to figure out the stability of a closed loop system. And they have this benefit that they not only can be used in the analysis, in the stability analysis of a closed loop system, but also they can be used for synthesis, for design of a controller, a good controller for our system. Okay? These three graphical methods include root locus method, Nyquist method, and vote plot method. Okay? Any of these methods has its advantage and disadvantage. For example, the root locus method is a very simple method. We can draw a root locus very simply. So it can be used very simply for analysis and for design of the controller. But it cannot be applied for any kind of system. For example, it cannot work for infinite dimensional system, you know. Infinite dimensional system like systems that have delay, okay? And they cannot be used for some complicated design, okay? And moreover, one of the other disadvantages of this method is that it is hard to represent uncertainty. By using this method, we cannot say that how much stable our system is. We cannot measure the relative stability of a system, okay? It is very hard here. What about the Nyquist plot? I mentioned that it is the most trustable and it is the most applicable method in control theory. It can work for any kind of system. It can always be used for example, finite dimensional or infinite dimensional, and it is very easy to represent uncertainty. We introduced some measures for computing how much the system is stable, which is called the gain margin and the phase margin. in the next lecture. You will be familiar with this criteria in the next lecture. And there are measures, I said, for computing how much is the relative stability of the system. And with the Nyquist plot, we can find phase and gain margin very easily. But the disadvantage of this method is that it is very difficult to draw. There is no set of certain rules that we follow to draw a Nyquist plot. Okay, and the other method is body plots. And body plots can be very easily drawn, but the disadvantage, the drawback here is that they may be misleading for some kind of systems. For example, when a system has some poles or zeros in the right half plane. When a system has some poles in the right half plane, we say that the system is unstable. And when it has some zeros in the right half plane, we say that it is non-minimum phase, okay? But this method is also easy to represent the uncertainties and to find the gain margin and phase margins. Okay, now let's get started with today's topic, that is Nyquist theorem. Our goal here is to count the number of poles of the closed loop system in the right half plane. Okay, based on the frequency response of the open loop transfer function. So we want to know how many poles a closed loop system have in the right half plane, considering the frequency response of the open loop system. Okay? There is a principle, there's a very famous principle, which is called the principle of argument, or the Cauchy's principle of argument, that gives us the idea behind the Nyquist theorem. It is a very interesting principle, I think. Consider a complex number on the complex plane. For example, an arbitrary s, and then compute g of s. And you know that g of s is another complex number which can be plotted in the complex plane as well, okay? So we can say that the image of this point under the function s naught, g of s naught, okay? Under the function g of s is something like that. Okay? So, now let's consider a closed curve, a contour, which is simple. When I say that it's simple, I mean that it does not cross or it does not cut itself. It is not something like this. It is not simple. Okay? And it is the boundary of a simply connected region. And it has a direction. We consider a direction for it. And we denote the direction by a small arrow on the contour. Right? So if we compute g of s, the function g of s, for all points on this closed curve, then we can find another closed curve on the complex plane. Right? Okay? So far, so good? Okay. So we can say that the second curve is the image of the first curve under the function g of s. Okay. Now, what does the principle of argument tell us? This principle relates the number of times that the second curve goes around the origin to the number of zeros and poles of the function g of s within the first curve. Okay? It's magical. Okay? So, and it is somehow related to what we want. We want to count the number of poles of a closed loop system the number of zeros, and we said that the poles of a closed loop system are the zeros of the function 1 plus k L of s. And this principle tells us that, I repeat again, the number of times that this curve encircles the origin is related to the number of zeros and poles of this transfer function inside this origin, inside this closed curve, okay? So here I give you a quick explanation, a quick proof for what happens here, but it is not applicable, I want to be honest, it is not applicable in, for example, in your exam question or when you want to use Nyquist plot and analyze the stability of a system. Just keep it in mind. I think it's very interesting and you should know it. Okay. In fact, what we want to do in this part is that we want to give, we want to provide an interpretation of what is an encirclement of the origin. Think a little bit of it in your mind. What we can say here is that the encirclement of the origin is related to the phase change of the points that moves along this curve. Okay. Consider a clockwise closed contour gamma, which does not pass through the origin. Okay. And this curve is traversed by a point S. Okay. For example, we there are two cases. We have two cases. The origin can be inside the closed curve, can be inside this contour, or it can be outside of it. Okay. We want to know in any of these two cases what is the net change of the argument of S. What is the total variation of the argument of the point as this point moves along this curve, okay, for both cases. Okay, let's start from this point on the closed curve. And then you can see that the phase is about 0 degrees, okay? Now, let's come down in this direction. And then, for example, for this point, we know that this phase has a negative value, for example, minus 45 degrees. And then we move along the curve, and you see that the degree, the phase decreases. Think of it as a continuous function, okay? And for example, here it's about minus 270 degrees. And now, when I come back to my start point, what would it be? Someone tells me? Yes. Minus 360 degrees, okay? And we can show it as a diagram. We can show the evolution of the phase as we move along the curve. We start with a 0 phase, 0 degrees, and then our phase would decrease, and eventually it gets to the point minus 360 degrees. Okay? Now, consider the other case, when our point is outside the closed curve. In this case, you can see that, for example, we can start from this point, okay, from 0 degrees. And then we come down, we go along the curve, And then you see that our phase decreases. But now when we go here, the phase would increase. You see that? Okay, and then you see that it increase to this point. Okay, and then it decreases again, decreases, and then comes back to the start point. Okay, and if we show the evolution of the argument here, we can see that we start with the 0 degrees, then we come down, and then we go up, and then come down, and eventually we reach to the start point. Okay. So in the first case, when the origin is inside the closed curve, we can say that the net change in the argument of the point as the point moves along the curve would be minus 2p, would be minus 360 degrees. Okay. But in the other case, when the origin is outside the curve, we can say that the net change in the argument of S would be 0. Okay, so it is a mathematical interpretation of an encirclement, a travel around the origin. Okay, so this is for one encirclement. What happens if we have a more number of encirclements? For example, we have n number of encirclements. In this case, we can say that the net change would be minus 2p times n. Okay. And notice that we care about the direction of the encirclement. If our encirclement is in the clockwise direction, then we count it as positive. And if it is in the opposite direction, in the counterclockwise direction, we count it as negative. Okay? So. Now for the origin, in this case, in this part, we consider an arbitrary number in the complex plane. For example, an arbitrary point. For example, a point that is denoted by r. Similar to what we said in the previous slide, in this case, we have two cases. R can be inside the closed curve, or R can be outside of it. And now, what we want to see is that what is the net phase change in the argument of S minus R, okay? What is the net change in the phase of the vectors drawn from R to the points S as S moves along this curve, okay? Similar to the previous argument, we can see that if R is inside this curve, the net change in the argument of S minus R would be minus 2p. And if else, the net change would be 0. Okay? So far, so good? Not any question? Okay. Okay. Now, now here, consider a transfer function g of s. We want to show what the principle of argument tells us. Consider this transfer function. It is given it can be written like this. And now we know, based on the phase rule, that the argument at the phase of g of s for any s is the sum of the argument of s minus zi minus the sum of the argument of s minus pi, okay? So now what we want to know is that the number of encirclements of this contour around the origin, okay? We say that the net change, here we have points S that moves along this curve, and here we have the image of the points S, which is G of S, that moves along the second curve, okay? We say that the net change in the argument of the points G of S here in the second contour is related to the number of encirclements of origin. We show that. And it is equal to minus 2p times the number of clockwise encirclements of 0 by this curve. Okay? Right? Now, we can write it in another way. We can compute it in another way based on this equation. We say that the net, we say that the net change in the argument of this function is the net change in any of these terms, in the argument of any of these terms, okay? So it is the net change in the argument of S minus Z1 plus net change in the argument of S minus Zn minus the sum of the net change in the argument of S minus Pi's, where Pi's are the poles, okay? So what is any of these terms? What is this? In the previous lecture, you saw that the net change in the argument of S minus Zi is either minus 2p or 0. It depends on whether Z is inside the curve or outside the curve, okay? So the sum of these terms would be the total number of zeros inside this curve. Okay? Right? Do you have any question? Is it strange? Okay. And for this term, we can say that it is equal to, in the similar way, that we can say that it is equal to minus 2p times the number of poles inside this contour. Okay? So this side of the equation said that minus 2p times the number of clockwise encirclements of the origin, which is denoted by n, is equal to minus 2p z minus 2p p, which is this term, okay? We can cancel 2p from the both sides, and so we can say that n is equal to z minus p, okay? So what does it tell? It tells that the number of encirclements of the origin by the second contour is equal to the number of zeros of the transfer function g of s minus the number of poles of the transfer function of g of s within the region that is enclosed by the first curve. Okay, right? So, the principle of argument, so it tells us that if we have a closed curve, we find the image of this closed curve, this contour, under a function g of s, okay? And then, for example, if we denote the first curve by gamma, we can say that the second curve is g of gamma, okay? And then count the number of encirclements of the origin by this curve, count how many times it goes around the origin, okay? And show it by n, okay? And it is positive if it is in the clockwise direction, and otherwise it is negative. And we can say that the number of zeros that the number of zeros of this transfer function inside this curve minus the number of poles of this transfer function within this contour equals to n. Okay? So, for example, for this figure, you can see that z is equal to 3. We have three zeros here within this closed curve, and we have 6 poles here, right? Okay. So we know that z minus p is 3 minus 6. That would be minus 3. And so we know that n is equal to z minus p. That should be minus 3. It means that we should have minus 3 encirclements of the origin. What does the negative mean? What does it mean?
Causal.
It's, sorry?
Causal, because if it would be positive, it would have more zeros than poles, so it would be non-causal.
No, I mean, what does it mean that if n is negative, n is the number of encirclements, z and p are the number of zeros and poles, okay? I mean, what is a negative encirclement? What does it mean?
Take counterclockwise.
Yeah, true. If we have a counterclockwise encirclements of the origin, we count it as negative, okay? So we see that we have we go around the origin in the counterclockwise direction 3 times, okay? So n is equal to minus 3, okay? So we want to use this. This principle to count the number of the number of unstable closed loop poles. Okay? So the function that we want to care about is 1 plus k L of s, whose zeros are the poles of the closed loop system. Okay? And we know that the poles of this function are the same as the poles of the open loop transfer function that we know it. Okay? And we want to know how many unstable poles, how many poles do we have in the right half plane in this region. Okay? So we can use the principle of argument in this case. And in the next part, we show you how we can define a contour that cover all the right half plane. Okay? Okay, we have only 3 minutes, I think, but I prefer to discuss the next part after the break. Okay? Take a seat, please. Settle down, please. Thank you for your help. Okay, let's go on. What we said in the previous part is about the principle of the argument, and I want to repeat it here. Okay. What does it tell us? It tells that if I have a closed contour in the clockwise direction like this, show it by gamma, okay? And then we find the image of this closed curve under an arbitrary function, which is a rational function. It has a numerator and denominator. And so the roots of its numerator are the zeros of this function, and the roots of the denominator are the poles of this function. Okay? It has some zeros, some poles, something like this. Okay? Inside or outside this contour. Okay? Now, if we find the image of this contour under this function, we may find some other contour like this that we can denote it by G of gamma. Okay? And we say that the number of encirclements of this curve of origin, which is shown by n, is equal to z minus p, where z is the number of zeros of the function g of s, the function that under which we find this second contour, within gamma, the first contour, and p is the number of poles in gamma. Okay? So, we want to use this principle to count the number of closed loop poles in the right half plane. So, here, this is the right half plane, okay? And what do we want to do is to count, is to figure out how many closed loop poles are in this region, okay? And use this principle. Now, what is the first thing that we should do here? We should first define a contour that covers all of this region, so that we can count the number of zeros inside this region, okay? But this is an infinite region, and it is very, maybe it is impossible to enclose it by a finite curve. So, we define a curve that has a D shape, and so it is called a D contour, and we choose a clockwise direction for it, like this. Okay? One segment of this contour is on the imaginary axis, and the other segment is a semicircle with a very, very large radius. Let's say the radius r, and r goes to infinity. Okay? Now, what is the function that is important for us to determine the poles of the system? What is the function that is zero are the closed loop poles? Can one tell me? We said that our transfer function, our closed loop transfer function, is something like k L of s over 1 plus k L of s, right? This is our closed loop transfer function. What are the poles of the closed loop transfer function? You know that the poles are the zeros of the denominator, okay? So this function is very important for us to determine the poles of the system, okay? So we can define, for example, G of S equal to 1 plus K L of S. Okay? And we said that L of S can be written as N of S over D of S. The zeros of D of S are our open loop poles, okay? And the zeros of the roots of nominator are the open loop zeros. We don't care about this part, just this part. Just consider this part, okay? So we can rewrite it as 1 plus K N of S over D of S, which would be D of S plus K N of S over D of S. Okay? So this function, the function 1 plus K L of S, can be written as this one. And it is a function, it is a rational function. It has a numerator and it has a denominator, okay? So the roots of the denominator, which are the poles of this function, they are not the pole of closed loop transfer function. These are just the poles of this function, okay? You see that this is the same, this is exactly the same as the denominator of L of S, okay? So we can say that poles of 1 plus K L of S are poles of open loop TF L of S. True? What are the zeros? What are the zeros of this function? We say that the zeros of this function are the closed loop poles, right? Okay? So the zeros of 1 plus K L of S are the zeros of closed loop system. Okay? So now this is the function that is important for us. And if we find the image of this contour that covers all the whole right half plane under this function, this important function, then we can find another curve, the image under this function. Okay? We may find another curve, for example, in this direction, okay, that goes around the origin n times. And if we count the number of encirclements of the origin by the second curve, by the image of D contour under this function here, okay, if we count the number of encirclements, which is shown by n, based on the principle of argument, we can say that n is equal to z minus p, where z is the zeros of this function, which are the zeros, which are our closed loop poles, our closed loop poles within this region, inside in the right half plane, and p is the poles of this function, which are the open loop poles of the system, which are unstable, which are in the right half plane, right? Okay, so far so good. So this is the idea behind the Nyquist condition, the Nyquist theorem. Okay, let's go on the slide. Okay, but so it is important for us to count how many times the image of D counter under the function of 1 plus k L of S encircles the origin. And we can rephrase this statement. We can say it in another way. We can say that instead of drawing the image of the D counter under the function 1 plus k L of S and counting the number of encirclements, we can draw the image of D counter under the function L of S, not 1 plus k L of S, under the function L of S, and count how many times the image goes around the point minus 1 over k. Instead of the origin, we say how many times it encircles the point minus 1 over k. Okay? Good. So we just translate, we are just translating the complex plane in this case. Okay. So what is the Nyquist plot? So I said that we find the image of this D counter under the function L of S instead of 1 plus k L of S. Okay? And it is called the Nyquist plot. And now we want to count the number of encirclements of the point minus 1 over k. Okay? Not origin. Minus 1 over k. And we can assume that k can have some different values. For example, for some small k, for some small positive k, minus 1 over k would be somewhere here. For an interval of k, it would be here, or it would be here. Okay? Okay, so the Nyquist plot is the image of the D contour under the open loop transfer function. And this is what our purpose was. We wanted to infer the stability of a closed loop system just by looking at the properties of the open loop transfer function. True? Okay. So, let's consider the Nyquist contour more carefully. Okay, thank you. The Nyquist contour has 3 segments here. As you see, one part of it, the segment 1, is on the positive part of the imaginary axis. The segment 2 is a semicircle with a radius that is very large. It goes to infinity. And the third segment is a negative part of the imaginary axis. It includes negative frequencies. Okay? And we want to find the image of this contour under the open loop transfer function, under the function L of S. And then we can compute the Nyquist plot. Okay? So, segment 1 corresponds to the point S is equal to J omega, okay, where omega is changed between 0 and infinity. It is a positive frequency. And so for this segment, for this part, we can say that L of S is L of J omega, and it is the frequency response of our system, okay? And we say that the image of this part under the function, under the open loop transfer function, is the polar plot. It is called the polar plot. Okay. What about segment 2? Segment 2 contains all points with a magnitude that is very large. Their magnitude goes to infinity. Okay. So it corresponds to the point to the points S equals to RE to the J theta, where R goes to infinity and theta. You see that it changes between P over 2 minus P over 2. For this point, 90 degrees. For this point, we have minus 90 degrees, okay? But for realizable systems, for physical systems that are causal, we know that the degree of the denominator of the transfer function is greater than the degree of the nominator, is greater than or equal to the degree of the nominator, okay? And so if the degree of the denominator is larger than the degree of the nominator, we say that the system is strictly proper. But if the degrees are the same, we say that our system is proper, okay? So for these systems, we can say that the image of the segment 3, these segments, would collapse on a single point. If the system is strictly proper, it would be the origin. It is very interesting that the image of all of these points would be only one single point. It would be origin if the system is strictly proper, or it would be a number on the real line, on the real axis with a finite value if the system is proper, okay? So we don't have any problem with the image of segment 2. What about segment 3? It includes the negative frequencies, and segment 3 corresponds to S equals to J omega, where omega changes between minus infinity and 0. Okay? In this case, we can write it in another way. We can write it as L of minus J omega, where omega is between 0 and positive infinity. And we know that since L is a transfer function with real coefficients, it has complex conjugate pair of poles and zeros. And so we know that L of minus J omega equals to, it is the complex conjugate of L of J omega, okay? So if you find the image of segment 1 for positive frequencies under the function L of S, for segment 3, we can just do a reflection about the real axis. We can just do a mirror image, find the mirror image about the real axis. So it is a very simple, it is too simple for us to find the image of this segment 2. Okay? So the only challenge for this D contour is the segment 1, or drawing the polar plot of the system. Okay? So what does the Nyquist condition tell us? It tells that if we have a closed loop system with a loop transfer function KL of S, which then if we find the Nyquist plot of the system, which is the image of the D contour under the loop transfer function, then we can say that the number of closed loop pose is equal to the number of encirclements of the point -1/k plus the number of open loop holes. Okay. What did we want to do? We wanted to count the number of closed loop poles which are unstable, which are in the right half plane. We wanted to find Z, okay? And we know P, because P is the unstable poles of the open loop transfer function. We know our open loop transfer function, okay? So we know its poles. We know how many poles does it have in the right half plane. So P is known, okay? So we draw the Nyquist plot of the function L of S, and we count the number of encirclements of the point -1/k, and we find n, okay? And when we find n, because we know P, by adding these two values, we can count the number of closed loop poles which are unstable, okay? So in order for a system to be stable, we want, for a stable system, we want to have Z equals to 0. We don't want to have any closed loop poles in the right half plane, right? Okay? So we can consider two cases. If our open loop system, if our open loop transfer function is stable, meaning that if P is equal to 0, okay, then in order to have Z equals to 0, what should be N? Zero. True. So in this case, we should not have any encirclements of the point -1/k. Okay? In the other case, we can assume that our open loop transfer function has P unstable poles, has P poles in the right half plane. Okay? So in this case, if you want to have Z is equal to 0, what should be N? Somebody, okay? Minus P, yeah. So we should have P encirclements of the point -1/k in the counterclockwise direction that interprets the negative sign here. Okay? Right? So far, so good. Okay. So, one important thing, one of our purpose is to counting the number of times our Nyquist plot goes around the point -1/k, right? So, how we can count the number of encirclements? It is simple for simple Nyquist plots for simple transfer function, but it may be challenging for some more complicated ones. Okay, but there is a very easy way to count the number of encirclements. For example, consider this Nyquist plot, okay? And here we can draw a line. We can assume that the point -1/k is somewhere here, or somewhere here, in this part, somewhere here, here, or here, okay? Now, if -1/k is here, then we can draw a line out from this point in any arbitrary direction. The direction is not important at all. So, for example, in this direction, I draw a line. And then, if I count the number of times that the Nyquist plot crosses this line in the clockwise direction and subtract the number of times that it crosses the line in the counterclockwise direction, then we can get the number of clockwise encirclements. For example, for this figure, you can see we have a crossing from right to left. So it is a counterclockwise crossing. And so we count it as -1. Okay? For point -1 over k here, we can draw this line. And so we see that there is no crossing, and so n is equal to 0. For this point, we can draw this line and see that n is 0. Here, let's draw this line. You see that we have this crossing from left to right in the clockwise direction. So n would be 1. And for the point here, you see that we have 2 crossings. Both of them are in the clockwise direction, and so n would be 2. Okay? Okay. Now we want to see how we can draw a Nyquist plot for a transfer function. We said that we have a D contour like this. It has 3 segments. Okay, so what we said is that the image of the segment 1 is the polar plot, is the frequency response of our system for positive frequencies. For this segment, there is no certain rule for drawing the image of that segment, okay? But we just want to plot L of j omega when omega is between 0 and positive 19, okay? So what we can do for this part, one thing that you should know is that you don't have to stress too much about the exact shape of our Nyquist plot. There are only 2 points that are important for us. One of which is the point that the Nyquist plot intersects the unit circle, which is the set of all points with a magnitude 1, and one of the other points is a point on the real axis that the Nyquist plot crosses. So the intersection of the Nyquist plot with the real axis. Just these 2 points are important for us, and we should compute them very precisely. But you shouldn't stress about the rest of the Nyquist plot, the exact shape of the Nyquist plot. We just want to count the number of encirclements, okay? What about the image of segment 3? We said that for physically realizable systems, they are either strictly proper or proper. If they are strictly proper, meaning that the degree of the denominator, which we can show by n, is greater than m, which is the degree of Okay, in this case, then we can say that the image of the third segment would be only 1 point, which is the origin, okay? But in the second case, we can say that it is a point on the real axis, okay? And for the second part, for the negative frequencies, we said that it is a reflection of the image of the first part about the real axis. Okay. So the 2 points that I mentioned that are very important to be computed very precisely, they are important for computing the gain margin, and phase margins. And I mentioned that these are 2 criteria to measure the relative stability of a system. We can say how much our system is stable, okay? And you'll get familiar with these 2 measures in the next lecture, hopefully. Okay, let's look at some examples. I prefer to use both. Our open loop transfer function, L of S, is a very simple one. It can be written, it is given by 2 over S plus 1, okay? So it has a stable pole. You see, in the S plane, that the pole is on the real axis with value -1, okay? So this is the single pole of the system. It has no zeros, okay? Now we want to find the Nyquist plot of this function. We want to draw it. Okay. We said that we should find the image of our D contour, and the first part is to find the image of this segment, which is our polar plot. So it corresponds to S equals to J omega, when omega is between 0 and positive infinity. Okay, so let's get started with omega equals to 0. We start from very small frequency. So if S is equal to 0, then substitute it into the function, into the open loop transfer function, and you get L of S what? 2. True. Okay. It would be 2. I draw the unit circle here. Okay. So we start from point 2. Okay. So we start from this point for omega is equal to 0. Okay. Now, what will happen if for very large frequency? I mean, if omega goes to infinity, you see that you have a strictly proper system here, right? So when omega goes to infinity, we go to the origin. We are approaching the origin, okay? So this point is for very, very large omega. Okay, but from which direction I go into the origin? This is important for us to determine the phase. Okay, the phase here. Now we can use the phase rule. What the phase rule tells us is that we can draw a vector from the poles and the zeros of the transfer function. For example, for one sample of the frequency here. And we can say that here we just have one.
Could you write a little bit bigger?
Sure. Sorry. Okay. We can say that the argument of this vector, if it is theta, then we can say that the phase of our transfer function at that specific frequency would be minus theta, right? Okay, so we'll start from this point. Okay, so we'll start with a phase which is equal to 0, and then we go up. Okay? So, for example, here, for omega equals to 1, we see that theta is what? It is 1, it is minus 1, and it is, in this frequency is 1. So what is theta? What? Yes. It would be 45 degrees. 45. Okay? So we can give some sample value of the frequency and find the corresponding points in the nitrous plot. So we can say that if omega is 1, we are somewhere here with the phase minus 45. Okay? And with the magnitude, what is our magnitude here? What is the magnitude of this vector? It would be the square root of 2. Okay? Yeah. And so when we substitute it into the function, you can see that it would be 2 over the square root of 2. So, okay? So the magnitude of our frequency response at this point would be the square root of 2. Okay? So we are here for frequency equals to 1. And then we increase our frequency. Okay? When omega goes to infinity, we see that theta goes to what?
Pi over 2.
Sorry?
Pi over 2.
Yeah, pi over 2. Okay. Theta would be pi over 2. Okay? So we go to the origin from this direction. From this direction. Okay? Can I ask you a question after? I'm afraid I do not have time. Okay. So our polar plot, we can say something like this. right? Okay? So this is the polar plot, which is the image of these parts. What is the image of this part of the decanter? We would say it would be the origin. Okay? What about this part? This part is for negative frequencies. And so we said that we just do a reflection about the real axis. Okay? So it can be done very easily. So we have this image here. Okay? So this is our Nyquist plot. Now we want to use this Nyquist plot to analyze the stability of our closed-loop system. Okay. Let's consider k is equal to 1. Okay. So what is minus 1 over k? Minus 1 over k point would be minus 1. Okay? So assume that minus 1 over k is somewhere here. Okay? So now we want to know for this value of k, if the closed loop system is stable or not if we have this Nyquist plot. What should we do now? We should count the number of encirclements of this point. Okay? What is the number of encirclements? How many times the Nyquist plot goes around this point? 0. So n is equal to 0 for this case. Okay? What is p here? The number of unstable poles of the open loop system. What is p? You should look at this function. You should look at its poles, and you should see how many of them are unstable. How many? 0. Okay. So what is z? What is the number of unstable closed loop poles? It would be n plus p, which would be 0 for this case. Okay? So if the point minus 1 over k is somewhere here, somewhere in this part, if minus 1 over k is between, the times is over, okay. So let's continue in the next week. Thank you.